All right, so this video continues with chapter 6, and we're going to look at 6.2, exponential functions. So for any real number, when a is greater than 0, a to the x is a unique solution. So 3 squared is different than 3 to the third. If you get the same answer, b and c have to be the same. If a is greater than 1, a smaller exponent means you get a smaller answer. And if a is between 0 and 1, a smaller exponent means a bigger answer. F of x equals a to the x is the parent exponential function with a base of a. On a graph, so let's look at 2 to the x. So 2 to the x is increasing, and it has a horizontal asymptote of 0. So the domain is negative infinity to infinity, and the range is 0 to infinity. That's when a is greater than 1. If a is between 0 and 1, so like a half, everything's the same except it's decreasing now instead of increasing. Your function capsule shows that when a is greater than 1, it's increasing, and these 3 points will always be part of the graph. So whatever that base is, so f of x equals a to the x power, that's the equation, those 3 points will always be on the graph. If a is between 0 and 1, it's decreasing. The same points are going to be on the graph. -1, comma, a to the -1, 0, 1, and 1a are always part of the basic exponential function graph. So remember, you can have this information on a note sheet for the test. Remembering your transformations. If you add or subtract a number to the function, you're moving up or down. If you add or subtract a number to the x, you're moving left or right, and it's the opposite of what you would expect. If you multiply the whole fraction, you're doing a vertical stretch or shrink, stretch. And if you multiply to the x, you're doing a horizontal stretch or shrink. And then a negative in front flips it. So the black line on this slide is 2 to the x. By putting a negative in front of the equation, we're flipping it over the x-axis. So the blue line is the negative 2 to the x graph. Here, we're adding 3 to the x. So we do the opposite, which means we would move left 3. So the black is still 2 to the x. The red one is the transformed line, 3 to the left. Here, we're adding 3 to the y, so we're going to go up 3. So the green function is that transformed function. You can use graphs to evaluate your exponential powers. So we could just type this in the calculator. We don't have to. Or we can say, okay, well, our equation is 2 to the x. And then we're going to try to find the value when x equals root 6. So to do that, you're going to use the second trace feature that we use all the time. This time you choose the value, and then you type root 6 in the x. If you go on Desmos, you're going to write your equation as 2 to the x. And then you're going to type x equals root 6. And the point where they meet is going to give you the y value. So that would be the value of the function. So if we do this on the calculator, I can make it work this time. All right, so I type my thing in. And then we go second, trace, and we're going to choose value. And this time we were looking for the negative square root of 2. So if I hit enter, go to. I typed minus instead of negative. This x value is negative root 2. The y value is what 0.5 to the negative root 2 equals. So that's how you can do that on your calculator. Desmos, you would put this is your y equals, and then in the next box you'd type x equals negative root 2, and then find the point of intersection. Solving. So to solve for an exponent, you're going to try to make things have the same base. So it's helpful to know some of your common squares and cubes. I'm going to set up a table and put it on there, but that would make your life easier. So the first thing you're going to do is rewrite these with the same base. So 25 is the same as 5 squared. So I can rewrite 25 to the x as 5 squared to the x. And 125 is 5 cubed. Now our exponent rules multiply those. So it's like saying 5 to the 2x equals 5 to the third. For those to be the same, the exponents have to be equal. So 2x has to equal 3. Divide both sides by 2, and x equals 3 halves. So if you can make those have the same base, you can solve for an exponent. So let's try this one. Remember, a fraction brings something to the bottom or makes a negative exponent. So this is the same as saying 3 to the negative 1 to the x. And 81 is 3 to the fourth. So this would be 3 to the negative x equals 3 to the fourth. So the exponents have to be equal. Divide by negative 1. And we get x equals negative 4. This one looks scarier than it is, but 1.5 is the same as 3 over 2. So I'm going to rewrite that. 27 is 3 cubed, and 8 is 2 cubed. So we can rewrite this as 3 over 2 cubed to the x, which would be 3 halves to the x plus 1 equals 3 halves. And then 3 times x is 3x. So those exponents have to be equal now that the bases are equal. Subtract x from both sides. 1 equals 2x. Divide by 2. X equals 1 half. That's how you do it analytically. Graphically, we can subtract this from both sides. So we would put in y1, 1.5 to the x plus 1. Minus 27 over 8 to the x. And then we would find our x-intercept. Second trace 0. We also could make this equal y1, this equal y2, and find the second trace intersection point. Multiple ways we can do it. So if we're solving greater than 0 or less than 0, we do the same thing. We find that x value. Then we use our graph or our intervals to check. So greater than 0 is this side. So for that to be greater than 0, it's negative infinity to 0.5, which is what we found that value to be. Less than 0 is the right side. So it's from 0.5 to infinity. So that part hasn't changed just because the equation has. So you try this one. Solve for x, and then look at it. So if we're trying to make our same base, 3 is already there, and 81 from before we said was 3 to the fourth. So now 2x is less than 4. Divide both sides by 2. When x is less than 2, this should work. In interval notation, that's negative infinity to 2. So if I were to graph this, it would be y1 equals 3 to the 2x minus 81. Let me go to my camera here. So I get that in there. Hit graph. I'm going to zoom out. And if we look, so we find that value, second trace 0. We pick a point to the left, we pick a point to the right, we make a guess. I didn't pick a good point. Second trace 0. Okay, I want to pick a point somewhere to the left. Pick a point somewhere to the right. Make a guess. 2. So that gives us our answer of 2, which is the same thing we got here, less than 2. So same process, whether you're doing it graphically or analytically. Try this one and then check for work. So 1/2 would be 2 to the negative 1, which makes this 2 to the negative 2x. 16 is 2 to the 4th. So this is 2 to the negative 4th. Now we're going to distribute our exponent. So we get negative 4x minus 12. Now we remove our bases since they're the same. So negative 2x is less than negative 4x minus 12. I'm going to add 4x to both sides. So 2x is less than negative 12. Divide by 2. X is less than negative 6, which means we would have negative infinity to negative 6 for our analytical solution. All right, looking at interest. So compound interest, interest equals principal times rate times time. A is the final balance. So in our years, we get an equation. So if you're just looking for interest, you can do PRT. If we're trying to do compound interest for a certain number of years, we're going to use this formula. I will give you these formulas on the test, so you don't have to memorize them. You just have to know how to use them. So let's try to solve. If 1,000 is invested, so that's our principal, at an annual 1.15 or 1.5%, so that's our rate turned into a decimal, so we have to move our thing twice. And then quarterly is 4 times per year. So that means n has to be 4 because it's 4 times per year. And then we're looking for 10 years, so that's our t. So we're going to plug those in. 1,000, 1 plus 0.015 over 4, because that's our n, and then 4 times 10 goes up here. You can type that right in the calculator, and it gives you 1,161.51. So that's the total amount in the account. So that's our total. So if we subtract the 1,000 that we invested, we're left with $161.51 interest. So if we were to graph that equation using our x for t, we could do our second trace value and put 10 in. We could use the table and go for 10. Either way, we get the same answer and then subtract our $1,000. Natural number e. So this is an irrational number like pi. It goes on and on forever. But e is what we use when we are doing continuous interest, like it's compounded all the time. That is PERT, P times e to the RT. So P is still your principal. R and T are the same thing. E is just what you use for the compounded continuously. So suppose $1,000 is deposited in an account paying 1.5. So it's the same interest rate as before. And we're doing 10 years. Let's plug that in. So 1,000 e to the RT, so to the 0.015 t. So that's our equation. How do we type that in a calculator? Well, in this calculator, E is down here with your ln. So I would type 1,000 and then second E. So some calculators will automatically put the exponent there. Other people need to use the caret. Either way is the same thing. But make sure you choose the lowercase e, not the capital one. Lowercase e. And then that was 0.015 times 10. So that's 1161.83. So we'd subtract the $1,000 and we'd be left with 161.83. If you recall from before with our quarterly, it was 161.51. So in 10 years, they got 32 cents more interest continuously. The more time that's in, the greater the difference you'll see, or the bigger the rate, or all kinds of things. But typically, in the same amount of time, continuous is your best interest. Calculator solution, same thing. You can do second trace, choose value, and then type the year, value, or you can use your table. All of those work to get you the same thing. Modeling risk. So let's say I give you an equation like this that is after age 40. So if we're trying to compare the risk at age 75 with age 40, the biggest thing is finding that difference. So when this is 0, so age 40, x would equal 0. So if you plug 0 in, anything to the 0 is 1, so risk is R. Well, at 75, you subtract 40, so it's 35 years later. So you plug that in, and you end up with 38.6 R. So that means the risk, these numbers, is almost 39 times greater when you're 75. So that's just a way in real life you might see this. So that's 6.2. Let me know if you have any questions.